Welcome everybody. Today we are very excited to have Camila Gonzalez present their work, Task-agnostic continual hippocampus segmentation for smooth population shifts. Camila is a PhD candidate at the Technical University of Darmstadt working on continual learning and out-of-distribution detection for MRI and CT scans. So very important and highly practical continual learning research. Camilla, we are very happy to have you here to close out the 2022 seminar calendar year. So please take it away.
Yes, thank you very much for that kind introduction and for allowing me to present my research here. So of course, I know that most of the viewers are very familiar with continual learning, but maybe not so much working with medical data. For me, it's usually the other way around. For my viewers, it's usually the case that they are very knowledgeable with medical data, but not so much continual. So yeah, I'm excited about presenting in this audience. Exactly, so I will just start. So very roughly what I will be discussing is I will start by motivating why specifically for medical use cases continual learning is so important, but also so problematic. There are certain issues that come up in medical that don't come up in other use cases. I will also talk about some practical considerations when working with medical data and trying to do continual learning. I'm referring to the regulatory perspective, also the economic challenges that come up, etc. And I will give a brief summary of sort of the risks and challenges of continual learning, but also the possibilities that this brings us. Afterwards, I will present basically the paper, which is the focus of this talk, which is this ODEx method for performing task-agnostic, privacy-protecting continual learning, which is a very, very simple method. I'm sure all of you will be able to grasp the central aspects. And then I will give some final thoughts and I will give an outlook of what I think is the future for continual learning in medical. Yeah, so starting with why is this so important? And of course, my thesis focuses on continual learning for medical. So why is this such a relevant topic for me and in general? Well, here what we are looking at is sort of the amount of practicing physicians shown as the surface of basically the area that you see in this map. So what becomes immediately obvious is, of course, there are regions where we have a lot of practicing physicians and also, of course, a lot of radiologists or pathologists. And then there are regions where it's very, very difficult to find an expert. This means that for medical, we have a lot of interest in really using deep learning to ease the burden of these physicians, to really give more access to healthcare to people who currently don't have it. However, as is the case with many other use cases, I would say, most of the research on deep learning for medical images focuses on this naive worldview where basically we have all of the data in one central location. This doesn't really change. This is data which remains static. So we train a deep learning model, then we deploy it, and we assume that the performance that model will have is similar to what we tested in this static setting. But of course, that's not the case. Particularly in medical, we have the case that we have many different institutions, we have many different vendors, we have many types of devices. We have a constantly changing population and constantly changing disease patterns. So how do we deal with these challenges? And what happens when we don't deal with these challenges? So you're probably familiar with this example for a software for diabetic users, where they were basically, this was one system that achieved very, very high performance in an offline setting. And this was a system trained with a lot of heterogeneous data, so a very, very large data set. Yet when it was deployed, when there was a study on the usefulness of this tool, of course, the results showed that the performance in the real world was terrible. And this is something that we see in many, many different with many, many different examples. And a central issue when talking about artificial intelligence in medical is that there are almost none randomized clinical trials. We have practically no prospective trials on medical. So what happens when the few ones that we do have show this catastrophic performance in the real world, and we actually have so few actual prospective trials? So you're probably all familiar with the problem of domain shift. So of course, the data that we use for training the model is very rarely the data that we will see during deployment. And there are a lot of shifts that can occur. In medical, I would say these are the central types of shifts that we see. We see a change in the vendors. So basically the vendors of the CT or MRT machines that are used for acquiring images. We see changes in the device depending on a specific model of, say, a CT. The images look very, very different. There are also changes in the acquisition parameters. When acquiring, say, a CT scan, there are a lot of parameters that are involved in this process. And this change quite frequently, I would say, even within the same institution. We also see changes in the reconstruction algorithms. This is a very, very big topic, and particularly because right now we are using a lot of deep learning for the reconstruction of these scans. This means that we are updating algorithms quite frequently, or at least we would like to update them quite frequently because we are performing better. So this is another facet where we have these shifts. Then we have, as I was saying, changes in the demographics of the population. We have changes in the disease patterns that occur. Consider, for instance, COVID-19. So what we saw for COVID-19 were patterns that were manifesting primarily in the lungs that were quite similar to pneumonia, but had certain characteristics that were not always the same as with viral or bacterial pneumonia, as we had seen before. So we have these new diseases, we have these diseases that change over time, and we have all of these different degrees of change that cause really our models to underperform in practice. And of course, a lot of these changes we can't foresee. So you may have heard about federated learning. I would say much more than continual. Federated learning is really taking central stage when talking about AI in medicine. So how does that work? Mainly we have the scenario where we have a lot of different institutions, as you see here, and the data cannot really leave the institution. The data must stay on each institution, but in a distributed fashion, we can basically train a model that leverages data from all of these different centers. And this protects patient privacy. This adheres to regulatory requirements for patient privacy. So yeah, this is, there was very recently a very, very large scale study with over 70 sites on federated learning for medical. This is something that right now is widely acceptable as a good solution for the problem of spatial constraints. However, we also know we have these temporal constraints. What do I mean with this? Well, the standard setting for continual learning is that we don't really have access to all their data. As the data distribution changes, I have to adapt to the new one, but I cannot really see samples seen early on during training. So this is where continual learning comes in. So as I was saying, the setting where most, I would say over 90% of all deep learning solutions are evaluated is the static setting where we have all of the data, which is just shuffled, and we just evaluate on a separate test set and maybe even in one out of distribution data set, but nothing else, no more than that. But the clinics are dynamic environments. We have all of these factors that are changing in the acquisition, in the patient population, etc. So these models suffer from data drift. And what we want to do with Continual is to be able to train the models sequentially. We can also think of this as accumulating knowledge over all of these different tasks. And again, most of you may be familiar with this concept, but what we want to do is to preserve previous knowledge without losing model plasticity. So if we see here, this is one example where I have a model that is very, very rigid. So I achieve some good performance on one of the first training stages. And then basically I keep training, and then my performance stays the same on the original data, let's put it like that. But then the performance that I get for further tasks decreases with time because this model is too rigid. And this would be an example of a model that is too plastic, where I can learn over time, so I achieve good performance or future tasks, but my performance deteriorates on older ones. So here I have the problem of catastrophic forgetting. Okay, so before I go into the methodological aspects, I would like to give you a bit of an overview of what the scenario is right now in terms of regulations and economic considerations, etc. So how does it work right now if I have a deep learning model, say, or just in general any AI system, and I want to deploy this within a clinic? Well, this is, first of all, the term that, say, the FDA uses for static learning would be a locked machine learning. So locked machine learning means the following. I first train my model with some data. Then I perform evaluation, and of course the evaluation should include evaluation on an external data set. So basically what you see represented here on this first color is sort of the domain. So you can imagine it as the vendor, and here would be the labels. So I do some evaluation, maybe also on an external data set, and then this goes through approval. So it goes through the approval process, which is a very, very costly process, and a process that takes a very long time, particularly for a new company. So after the software has been approved, we can actually deploy this model. And during the deployment, of course, there may be some errors, and particularly because I have all of these changes in the data, over time, I will have more and more errors. So what is it that we want to do with Continual? Well, this would be this other perspective where this stays the same. So basically, I would have a model, I would train it with some initial data, and I would evaluate it. And then before approval, I would also define exactly how I plan to change the model. So this means how I will acquire the data for training it, how I will perform quality assurance on the data to make sure that it will be helpful for my model, etc. So I will define all of that. Then I go through this approval process. And the advantage now is that I can do, say, active learning, where when I get these errors, I can acquire new labels and I can update the model. And of course, this would probably require more quality monitoring. So this perspective that you see here is not what is currently the case. Right now, it's very, very difficult to deploy a continual learning system without going through a new approval round every time to update it. This is the perspective that we are seeing on certain documents that regulatory bodies have released, but that are not yet represented in regulations. You may have heard about the medical device regulations. This is a big, big change that's coming on a new regulation in the EU. And this is particularly causing a lot of practical issues, I would say, because you have a high number of products of, as we say, software as a medical device that have been approved with previous guidelines, and now they have to adapt to these new medical device regulations. And for this, they need to go through a process that is very, very backlogged because you have such a big amount of companies that want to revalidate their products. So we will probably see what we will probably see is that the deadline for updating those products to the new regulation will be extended for a few years. But even then, what we are seeing right now is this transition, which is causing a lot of problems in the industry. And according to this medical device regulation, it is in particular quite tricky to update models. Okay, so very briefly, because I guess all of you are familiar with this, what are the opportunities and also the challenges of continual learning? Of course, the main opportunity is that I can adapt to changes in the domain. As my data changes, I can adapt to these changes. I can achieve forward transfer, where my model even performs better on tasks that I learn afterwards. And of course, this is the goal that we are all changing, and that seems even now so far away, which is backwards transfer, the situation where my performance on even older tasks actually improves as I continue training. And then what are the challenges? Well, catastrophic forgetting, we are all familiar with this concept. The fact that failures can be incorporated. So this is, imagine the situation where software is deployed in a clinic, and then new annotations have to be gathered on this particular clinic. How do you actually make sure that those annotations are correct? And we may also be retroalimenting biases. For instance, there may be certain conditions that are very, very rare, certain kinds of tumors, say, that are very, very rare. And in the initial training phase, I may have made sure that I have enough representation for these conditions, but I have no guarantee that I will continue having that representation as time goes on. So I have a change also in the class or label distribution. So I have all of these possible risks. But we still believe, or at least I still believe, that it makes sense to try to achieve robust continual learning. Also, from an economic perspective, if we need to go through a new reapproval round every time our model is updating, this is a very, very costly process, and this is often not possible in practice. For instance, according to the FBA, I was just recently at the RSNA talking with a lot of companies, a lot of startups. One of the considerations of the FDA when updating a model is that the performance has to increase across all of the seen findings. So say if we have a model that detects 200 possible conditions, then as soon as my model decreases in performance for one of these conditions, I cannot update the model as easily. I have to go through a very costly reapproval process. So just to, if we really want to have systems that are, that in practice make sense from an economic perspective, from a safety perspective for the patients, we need to be able to adapt this. But yeah, we need to keep in mind that all of these risks are possible. Okay, so after that introduction, let me get on to the content of the paper that I'm presenting right now. So what we see for a lot of methods, of a lot of continual methods that are out there, even some that are state of the art and that perform very, very well on, say, CIFAR, permuted MNIST, etc. What we see when we apply them to medical data, say medical image segmentation, is that they don't perform that well in practice. So they are either too plastic or too rigid, or the training times and GPU memory increases quite linearly with the length of the data stream. So when working with medical data, you should always consider, at least, of course, there are many types of medical data, but with working with, say, MRT, CT scans, you should consider that these are very, very high dimensional images. So say for a thorax CT, I'm talking about around 512 times 512 times 200. That is the resolution that we're working with. So you can imagine how difficult it is to pack these things into the memory, and how computationally expensive it can be to deploy a lot of the methods that are out there for continual learning. So this is really the situation that we see in practice. It's either not possible to deploy some methods, or they just don't really achieve as good on all of the seen tasks. So there is one class of methods, which is these expansion-based methods, where basically I keep adding parameters to the model or say in the simplest case, I keep an ensemble of models where I basically just grow this ensemble pool. So this class of methods have a lot of advantages in practice. For instance, when doing medical image segmentations, the models can be quite tricky. So a lot of methods that are out there cannot be binded into that architectures easily. Here, this is something that I can do, quite easily. Then if I keep this perspective of just having, say, an ensemble of methods, okay, then of models, sorry, then at least one of those models will always perform well regardless of the task. So this is basically a class of method that I think in practice works quite well and makes a lot of sense for medical data. However, when talking about these expansion-based methods, we often take the perspective when we have clear task boundaries and defined task labels. What do I mean with this? Well, clear task boundaries would mean that, say, I have data coming from task 1. You say here, imagine, for instance, I have data coming from a particular scanner. Then there is a change in the scanner, so I start working with data from the second scanner, and then a third scanner comes in, so then I just always change with that data. This would be having rigid task boundaries. The opposite would be when I have slowly changing shifts, such as, say, okay, there are a lot of parameters that I am using for my image acquisition, and some of these are changed maybe just a little bit over time, and then I also have other factors such as the patient population very slowly shifts towards older patients, and maybe I have certain conditions that become more represented in my subject pool. So then I have a lot of these changes that just slowly change over time. And you can imagine this is a very realistic situation. And here I would be dealing with these smooth task boundaries. Then the difference between having task labels and not having them is when during deployment, I know where an image comes from. So I know if it's like from task 1, from task B, task C. In our example, it would be from scanner A, B, C. If I have this information, of course, the simplest way of doing an expansion-based method is, okay, depending on where that particular image comes from, I use one particular set of parameters. But what happens in this task-agnostic scenario where I have these smooth changes and I also don't have task labels? Well, in that case, I have 3 additional challenges. I have to first detect when such a domain shift occurs. During inference, I have to be able to choose the best model. And I also need to keep this model pool small, or this parameter pool small. I can't just keep increasing parameters as time goes on, because then, of course, it becomes too, I would need too much storage. So how do we approach this in this particular example? Let me actually look at the time. Oh, it's fine. Okay, so how do we approach this? Well, as I was saying, so consider the most basic, the most simple expansion-based strategy where I just have a set of I have basically a set of model states, or I have a set of parameter sets. And I have one for each of the learned tasks. Then if I have such rigid boundaries, then I can say, okay, so I initialize my model as I regularly would. Then when there is such a change, I initialize a new model. And then again, when there is a shift here, I initialize a third model. And then during deployment, using these task labels, I decide which model to use. So this would be basically the simplest way of doing expansion. Now, how do we at least approach this in a task-agnostic fashion? So, as I was saying, we have these 3 additional challenges. So what we do in this case is to always monitor basically certain features. And these are features from the first batch of batch normalization layers, which we know have a lot of properties for detecting particularities in the domain. So what we are looking at is these features, and basically we extract these features from the model. And first of all, with say the initial data that we have for the model, we estimate a Gaussian distribution over these features. So then later, as new data comes on, we can calculate the distance. In this case, we calculate the Mahalanobis distance to the previous distribution. So say we start here, of course, this is just my initial data. So then I initialize a model state and I say, okay, so there is a certain mean a covariance matrix that explains the distribution of my data. Then as a new data batch comes, I can calculate the distance to this distribution. And if this distance is low enough, I just say, okay, so I can keep training this model. Now, when this distance is too large, when the distance to my training distribution is too large, I realize, okay, now is the time to initialize a new model. So that's what I do. I initialize a new model and I maintain this model and the new one in my model pool. Then, well, you can see new batches come and I repeat the same thing, only I always take the model for updating that has the lowest distance. And then at the end, during inference as well, I basically calculate this Mahalanobis distance to all of the models in my pool, and I just select the one with the lowest distance, and I use that for extracting, in this case, the segmentation mask. Now, there is one particularity when we do this that is, okay, but I cannot calculate the covariance on all of the data, like say all of these orange points that you see here, because of course I no longer have access to that data. And I may not even have access to these features. So considering that, what we do in this method is that we keep this, say, model history, where we just keep the distributions that we have seen over time. So basically we accumulate the mean and covariance, and then we calculate the distance to the sum of all of them, or to the average of all of the distributions. Okay, and how do we evaluate this? Well, for this work, we cooperated with a neuroradiology clinic in Mainz. So we are working on hippocampus segmentation. So this is hippocampus that you see here, and these are the segmentation masks that we want to use. And basically what we do to create these scenarios of slowly shifting demographics is that, first of all, we take data from 3 different sources. So these are 3 openly available data sets, Harpy, Dryad, and one from the medical segmentation decathlon. And we basically just change how many samples are in which task. So first we only have data from Harpy, this decreases, then we have some cases from Dryad, and then at the end we add cases from Decathlon. This is one of the settings that we explore. And for the other one, we wanted to have a little bit more control of seeing what are the actual changes that are going on. So here we introduce synthetic transformations that we achieve with this Torch.io library. So we change the contrast of the images, we do certain translation changes, change scaling, rotation, etc. So these are our 2 scenarios, and this is just so that you get a little bit of a picture what sort of scores we can get. This is basically what you see in this diagonal is what happens if for one particular task I just train a model statically and test it on the test set. So here you can see we have dice scores. So dice is a measurement of overlap that we use for segmentation. We have dice scores of around 90%, which is common for hippocampus segmentation. And then when we use basically a model from another task, like say in this scenario, we use the model that we see right at the end of task 1. You see that, say, on the last task, we only get a dice of 0.9. So we have, so we have a very strong shift there. So you may see a few more results in the paper, but here we are comparing, say, with elastic weight consolidation, which you may all be familiar with, and with modeling in the background, which is an approach specifically designed for segmentation. And what we see here is that elastic weight consolidation on this particular Haben parameter setting is quite rigid. So here we see the performance from task 1 to task 5. So what you see here at the start, so elastic weight consolidation is able to maintain quite high performance on the first task. And then because it's too rigid, it's not able to learn for future ones. Opposite to that, we see modeling the background. Modeling the background is a method that is too plastic. So what we see is that it achieves good performance on sort of the last few tasks, but it forgets catastrophically on the first ones, as you see here. And this is our method. So by doing this expansion-based solution, we don't really lose plasticity because, of course, we don't lose plasticity. We are always initializing new models. And we also don't forget catastrophically because we maintain these older models, say, that we learned with the initial tasks. We also did a bit of an evaluation when we compared different settings of our method. So this is, for instance, the case where we would have these rigid boundaries. So we know we have 5 tasks. We know these boundaries. So this also means that we have 5 models here. And you can see that the performance is very, very similar to the method. Here, it actually performs a little bit worse. So this means the method that we use for selecting which model to train and also for selecting which model to use during deployment works quite well. Here you can see, of course, how many models we actually have at the end. And you see that for this case, we only have 2 models. For this case, we only have 4. So this would be one consideration where we are looking at the decrease in the dice score. So this would mean the decrease, say, in the loss during training. Basically, when I find that the loss has decreased too much, I use that to detect a boundary during training. And you see this performs just a little bit worse. We also see here the perspective without this buffer. So basically, when we just take the data distribution of the last batch for a particular model. And here we see that we have a very, very clear deterioration in performance. And this happens because we have these slowly shifting changes. If we only take the distribution of the last batch, then this is not as different to the distribution once a shift has occurred. So what we see here in this particular case is that we only have 1 model at the end. And this is the gram matrix method. So this is a method that basically also looks at features and calculates a different kind of distance. So yeah, you see this is a very, very simple solution, but that performs quite well in practice. And of course, the main critique of this type of method, why people don't often do expansion-based, is that they say, okay, it uses a lot more resources. Well, what we actually see, of course, is that we do need a bit more of persistent memory, but this is not really a limitation, particularly when we're talking about hardware that is found in clinics. I mean, really, each model state, even though these are very, very large state-of-the-art image segmentation models, each model state requires less than 200 megabytes. So if we are able to really tamper the size of the model pool, as I was saying, this is not really a concern in practice. We also see that we don't really have additional training time. So what you see here is compared with just regular sequential training. We see that our method needs only minimally more in only minimally longer trainings. And this comes just from the calculation of the covariance matrix that we need for calculating the distance. And why this takes so little time is because we take features in a low dimensional space. So then calculating the covariance doesn't take too long. We also do that in the CPU. So we don't even need more GPU memory, which is a big build constraint when working with medical data. So by just taking this very, very practical solution, we are able to sort of land here when we have a model that is rigid enough, still plastic, and that doesn't use too many resources compared to regular sequential training. Okay, let's just take a look at some qualitative images. So what you see here is the ground truth. So this is the ground truth annotation of the hippocampus. And this is one subject from the first task. So this is basically a subject from Harpy that we saw very, very early on during training. This is a test subject, not a trained subject. And you see here that actually the segmentation model manages to do a segmentation that is better than the ground truth, because we have these artifacts coming just from the annotation tools that you don't see here in the segmentation produced by the model. But then, of course, as I continue training my model, this segmentation really deteriorates. And particularly in image segmentation, we see this very, very clearly, whereas, say, in classification, we cannot really see the effect of catastrophic forgetting as clear. And here you see what happens when we use a lot of different methods and what we use when we use ODEx. So in this particular case, say, ODEx manages to identify, okay, so it's really, I don't remember if the first or the second model state that is best suited for segmenting this image. So then I managed to get this very, very smooth segmentation, whereas these other methods fail. Okay, so that was a little bit on the method. Of course, if you have any other questions, please feel free to post them or just reach out. So yeah, what does this mean? So just basically summarizing and giving a little bit of an outlook. First of all, as I was saying, what can we do when we can do continual learning in medical? Well, we can do basically this active learning setting, which is very, very interesting, where basically we have a radiologist, in this case, a pathologist, etc., just a professional that is labeling new data, and we can put this back into the model. And there are many techniques to even make this labeling process a lot more inexpensive. Like, say, this is one method that we developed where just by segmenting just very, very few slices, you're able to get very high quality segmentation masks that you can use to improve on your training. So yeah, it's really, we have a lot of motivation to enable continual learning in medical. I also want to point out, if you're interested in working with medical, we have a lot of open source projects where you can try out, say, extracting saliency maps. And this is actually the project for which we made the experiments for this paper, lifelong NN unit, that you can use if you're interested in image segmentation and want to test different methods for continual learning. Then please, yeah, let us know and try this out. There are also a few more projects on this scenario. So coming to the conclusions, as I was saying, there are many factors that cause this data drift problem with medical data. We have changes in the acquisition equipment, in the vendor, in the patient population, and this causes data drift. Now, we really believe that continual learning is needed for safely deploying AI systems, and also do that in a way that is economically feasible, in particular for smaller companies that are trying to sell their AI algorithms. This is currently not possible, or it's very, very difficult, but we can see from a lot of documents that have been released that there is active interest in making this possible and really writing regulation that is consistent with what we know on continual learning. Now, there are a lot of clinical environments that are dynamic, but also task agnostic. So a lot of the methods that we know for continual learning that use these rigid task boundaries and that use task labels during inference, we cannot use them directly in these scenarios because we don't have labels. We have a lot of factors changing a little bit over time. And this method that we are validating in this particular paper is a very, very simple method, but that really preserves the knowledge without losing plasticity, that allows us to get coherently looking segmentation masks, and that also has low training times and no additional GPU usage, only at the cost of a little bit more persistent memory. Yeah, I would say basically the main message that I would like to give, or at least my perspective, is that really one of the central challenges when doing continual learning is detecting these changes in the domain, so these domain shifts. If we are able to detect this, a lot of the problems that we have with continual would be solved. And in particular, expansion-based methods are simple, very flexible, and even easier to regulate potentially, because if we actually keep the final state of certain models, then and choose train new models, then it may even be easier to regulate such systems. Now, for future work, or I would say now current work, because this work is now a little bit old, what are we working out? Well, of course, validating this in other anatomies and modalities. For instance, we found that with prostate segmentation, we get very, very similar results. Also looking at ensembling techniques here in inference, so not just using one model, but just ensembling, and only keeping certain parameters domain specific, so only keeping some task-specific parameters, and then keeping some which are shared. And the ones that are shared could be, say, the first layers of the encoder, or everything other than the batch normalization layers. There are different settings that we are testing. And we hope that just with these simple changes, we may even see a situation of backwards transfer. And we did see actually backwards transfer even with this method for some cases, where a model that is trained further performs better, so gets a better segmentation than the one right after training that particular task. Yeah, so this was, I guess, my presentation. So yeah, please let me know if you have any questions. And I know, of course, a lot of people may watch this talk later on. So if you have any questions, please reach out over Twitter, email, wherever you want.
Thank you, Camilla. That was a great talk, and I have quite a few questions for you, if you do not
Nice.
mind. So first question, which I think you kind of talked about in your final thoughts and remarks, but you opened up with the motivation about needing approval for these models and everything being very rigorous and time consuming for a good reason, for safety reasons. So is the end goal, I guess, because the way I'd imagine now is with your approach, you would need every new parameter to be reapproved with the expanding model. So is the end goal to say to get approval, I guess, of the continual learning model, like so some type of approval such that every time you add an expansion in your method, it's already pre-approved, I guess, or a lot easier to approve. Is that kind of the end goal?
I mean, that was a little bit some thoughts that I have, but of course, in the particular, currently the way the method works, I would still be updating the models as time goes on, so this is not the case. But I just imagine that if we have such a method that where you get more models and you don't really keep updating older models, so you say, okay, so I have a model freeze on one particular time step, then it may be easier to reach a regulatory protocol where those models remain static and I only need to validate the new one. So in that case, I can imagine a two-step validation process where first I say, okay, so this new model that I'm introducing here performs better in these situations, but a little bit worse for this situation, or say for these particular findings. But then I say, okay, but then during deployment, I maybe for this particular finding, I would just use this other model, or I would say what output I get from the older model and for the new model. I mean, there are different, I suppose there are different perspectives of how we can approach it, but I can imagine this may be easier to regulate if I basically add a new model to my framework.
That makes sense. I also thought a lot about the newer problem called model editing a lot in your talk. I'm not sure if you're familiar with that, but I wonder if sometimes it's just the simple fixes that need to be changed, like localized edits, and whether or not those could be easier to pass through regulatory barriers. Um, but another question kind of related to that. So my understanding of your method is, starting at the beginning, you have this type of um, uh, features that that batch normalization layers and such that you're using to detect drift. So I guess my question is, do you start with a randomly initialized model, or is there some sort of pre-training that boosts, I guess, the meaning of these features?
Oh, yeah, that's a good question. So actually, no, we just start with a model, I believe, initialized with Xavier initialization. So we use this NNUnit framework, which is an openly available pipeline that is state of the art for many of these medical segmentation problems. So we just use a standard initialization there, which I believe is Xavier initialization. So the particular, I mean, these cases of prostate and hippocampus segmentation, these are problems that are considered quite, I would say, quite easy in the sense that with not such large data sets, you can get good performance. At least you can really get your model to converge to acceptable performance. So for these particular cases, I don't think we would see a difference here by pre-training um, by doing other kinds of pre-training, but of course
Okay.
that's something that would make sense to try, and that is a setting that we do take for some other types of images and for some other types of problems, such as say for thorax CT and for detecting pulmonary emboli in thorax CT. Then we do pre-train with sort of larger data sets. So whether with this I would be able to get, I guess your question is, more expressive features. Yeah, that's a good question. I mean, it's
Yeah,
not
and
something
that
that we looked at.
particularly mean, I guess, for like distribution detection early in the early stages. Um, I don't know if that'd be uh, helpful or not. So just being able to, if you have distribution shifts pretty early on, I would imagine having a good starting place for features could help, but maybe not for this particular problem.
No, but definitely. I mean, I also suppose, I mean, for certain cases where annotations are very, very scarce, I can say if I have a model that was trained with, say, a lot of thorax CTs, but for a say for long segmentation, I mean, I have a lot of data for long segmentation, so I can train a model for long segmentation with a lot of thorax CTs, and then say, okay, what I actually want to do is to segment some type of lesion or some type of nodule or something. But then after having done this work, then I already know what sort of features I would be expecting just in general for thorax CT. And so then from the start, I would be able to detect when I have a deviation from this in my new data
Okay.
for my actual target task. So no, this makes perfect sense for a lot of use cases. Yeah.
Great. And last question, and this is probably may not be a good question, but a lot of times us working on what you might call toy problems, just classic image data sets, get questions from reviewers such as, "Have you tried it on real data?" So I'm wondering, do you ever like have the flip side? Do people ever ask, or do you ever experiment with using, some of the toy data sets like CFAR or ImageNet in your development process at all, or when you're like, are methods robust to other things, or is that something in the medical imaging domain that you just completely ignore?
No, definitely. I mean, we definitely do that because I mean, for a lot of methods, we first, I mean, with this, we did some experiments with a lot of methods that are also more complicated or that would require much longer training. In particular, we do that a lot. That we first work with, yeah, with different types, also with these permuted cipher data sets. We worked a lot. So a lot of things we try out first with these sort of small two-dimensional images, just to make sure that it works. And then often even, okay, so using these sort of toy data sets, but with a lot lower cases, because I mean, what we have in medical is that from the one side we have a lot much higher resolutions. On the other hand, we have a lot less subjects, so our data sets are much smaller.
Mm-hmm.
So we do that a lot of taking these data sets and also just taking less images from these data sets and trying things out there. This is something, yeah, we do a lot.
Great.
And I mean, it makes perfect sense
Yeah.
because I mean, yeah, it allows us to very quickly find out when something is not working out at all.
Weird.
And we do also get very similar, so we could get a similar criticisms from reviewers. For instance, when we always have the problem of either working with open source data, which allows for reproducibility, but then when we work with open source data, we are also not so sure what are the factors that are different from dataset to dataset. Like a lot of the work that I do for Continual is okay, for the same sort of problem, I take 3 or 5 openly available data sets, and I see yeah, how basically this changes. But then you have the problem that you don't know what are all of the different changes that happen between those data sets. You don't know if I mean, you usually know, okay, which devices were used for acquiring the images, but you don't know exactly which images which is which, with each device. You know maybe the mean and standard deviation of the age or the gender or these sort of demographic factors, but you don't know per subject what's the situation. So working with openly available data, you don't know a lot of these aspects that will be very interesting to look at. And then if you work with in-house data, you know all of this information, but you
Can't
can make
reproduce it.
your results. Yeah, you can reproduce it. Yeah. So yeah, so I would say with some works, especially for journals, like at least one journal where we do something similar for auto distribution detection. What we did is, okay, we do a little bit with in-house data, and then a bit with openly available data.
Okay. Well, that makes sense, and thank you for doing that hard work because it sounds very complicated.
I would also say, like, in terms of sort of what are dummy data sets for us, I would say even like the case that I'm showing now for hippocampus segmentation, because of course this sort of thing we are doing with a lot of different problems. I would say hippocampus segmentation is one good place to start if you're interested on trying things out in medical, because the images are lower in resolution. We are talking about maybe a 64 times 64 times 64, and you have a lot of openly available data, and so you're segmenting the hippocampus, not a certain lesion. So this means you always have exactly one hippocampus, one connected component on each image. So these are things that yeah, we also look at with first when developing a method. We often maybe try out which data that has these characteristics.
Thank you for all of that, and I'm sure everyone listening or listening at a later time will really appreciate it. One TLDR there is this, would you call the hippocampus segmentation the CFAR-10 maybe of medical data?
Oh, I would say yeah, maybe the C400. So
CFAR.
I would say maybe there's also this MetMNIS dataset
Yeah,
that
yeah, yeah.
can be
Okay.
used for benchmarking. So I would say that would maybe be the MNIST of
Okay.
medical.
Great. Well, thank you everybody for joining today. Thank you, Camille, for this presentation. I thought it was a great way to end the year. I learned a lot. I actually took notes during your presentation, so thank you.
Oh, nice. I'm
And
glad.
I guess that will wrap up our seminar series for 2022. Look out for some changes in the Continual AI seminars for the 2023 year. We have to keep things exciting and new and different. So if you want to stay updated, subscribe to this channel, join the Continual AI Slack, or the Continual AI newsletter. And I guess we will see everybody next year.